our recent research in our attempts to build some Bayesian reformulation of a well-known representation procedure known as batch normalization, which is efficient but yet awkward. And we tried to reformulate it in order to make it well, more mathematically attractive. So, what we have obtained, Andrew will tell you about it.
Thank you for the introduction. Hello. Today I'm going to tell you about our work with Arsenij Shuha, Dmitry Molchanov, Kirill Nekrudov, and Dmitry Vetrov, which called uncertainty estimation via stochastic batch normalization, where we try to investigate batch normalization technique. Firstly, I would like to provide you, to recap batch normalization technique and provide some intuition behind that, and why try to understand why it actually accelerates training of deep neural networks. So then I propose you a probabilistic model, probabilistic view on batch normalization, and address one inconsistency in batch normalization between train and test phase. Then I will propose you an approximation technique for inference stage, which is provide a scalable method for uncertainty estimation, and overview the results. So let's move on to the batch normalization. So the batch normalization layer looks as follows. Take the batch of input and compute the mean over the batch and the variance, and normalize all inputs in the batch so that they have zero mean and unit variance, and in addition multiply by gamma and add beta to not restrict the
expressivity.
Yes, thank you. On the test phase, batch normalization, instead of statistics over the batch, use running average statistics, which can be seen as an approximation for population statistics, and they estimated using exponential smoothing during the training as follows. Why this technique actually helps and accelerates training of deep neural network? So the authors of this method claim that batch normalization addresses so-called internal covariance shift, which looks as follows. Let's consider the deep neural network with 90 layers, and let's consider the last layer. So to train neural network, we take a batch of inputs and pass them through the network. So and the input to the last layer, actually the distribution over one hidden unit over the batch looks like that. So we pass them through the last layer. We fail because we want to start training. So we compute the gradient with respect to all parameters, and update all previous layers and that layer in direction of our gradient. So then we take another batch of objects, or we can even take the same batch. And since we update all previous layers, the activation of the same hidden unit change a lot. So, and our last layer confused, and it failed again. So it didn't see this data from the domain yet. So, and again we fail, and it cannot handle it. Cannot handle it. So it's look reasonable, but I would like to show how it works in practice on two examples. So let's consider the simple neural network have x as an input, we multiply it by a, which gives us the first hidden representation HA, multiplied by b, c, and there is some loss function as end. So
there are nonlinearities.
there is no nonlinearity. It's a simple linear neural network.
Do you consider one-dimensional case? Do you consider one-dimensional case?
Yes, this is scalars, also scalars. And let's take the derivative of our loss function with respect to parameter a. It looks as follows. dl by dhc times dhc by dA. So,
And whereas DHC with respect to HB, and HB with respect to HA, and HA with respect to A.
why? Well, it's,
No, this is of course correct, but this is not full decomposition according to
yes. And it's equal to dl by dhc. And dhc is simple xa, b, c. And the derivative of this guy with respect to a is simple x, b, c. So we can see that the derivative of our loss function with respect parameter a depends on all other parameters, b and c. And gradient descent is completely blind to this information, to this interaction between the variables. And that's why second order dimension optimization algorithm applied. So we can take the derivative of our derivative with respect to b, but it still will be dependent on c and other parameters if we have deeper neural network. So, and because of that blindness to curvature of our loss function, to the second order and to higher order interaction between the variables, gradient descent stuck and fluctuated.
Wait, I still can't see any. Well, I can't still see problem. So the gradient with respect to A depends on B and C, and so what?
Yes, and if, for example, B is very high, we have very high gradient with respect to A, and if one of B or C is very small, the gradient is also be very small.
Yes, but this is true. It should be
Yes.
small.
So, but
But if it's
Okay.
small, okay, we'll have some problems with the convergence. So the optimization algorithm will be very slow. Okay.
and let's put a batch normalization layer between all intermediate layers. Times A batch normalization. And so on. And the batch normalization here will look as follows. Without a fine transformation, we subtract the mean of our activation HA and divided by standard deviation.
Compute it with respect to mini batch? With respect
No,
to the whole
no,
set?
let's consider the case where population one we compute. So, and if we now take the gradient of our loss function with respect to parameter A, it's equal to dl by dhc, dhc by DH A decomposed in this way. So, and let's consider the last guy here. And HA equal this guy, and we can see actually that this guy here HA is x times A minus times expectation of x divided by A times square root of variance of x, and A disappear, and this is equal to 0.
You mean expectation of this?
If you compute it with respect to the whole set of objects, yes,
Yes.
you will obtain 0.
In expectation.
Because this guy doesn't depend on A. We compute the gradient.
Right.
Okay. And okay, and we and this equals 0. And so.
But this isn't what we want, right?
What we want, the gradient of our parameters doesn't depend on
Scaling factor.
another parameters.
No, but it doesn't depend at all on scaling factor, right?
Yes.
If you insert Bayes normalization layers, then your output is independent on some multiplications on scalar
Yes.
somewhere inside.
It will depend only on the last layer.
Yes.
And
So why
and-
do you put gamma as a multiplier in Batch norm when you only need it in the last layer?
no, I didn't get it.
Get back to the previous slide where you have the batch normalization formula. It has learnable parameter gamma, which
Okay.
controls the magnitude of your activations. But then the next layer after batch norm, you'll get rid of this scaling factor.
In this case, yes.
So why use it anywhere except the last layer?
We don't use it here.
No.
It's
The
I mean,
question
in
is
the
about
batch
general
norm,
scheme.
in the original
The general
formulation.
scheme, you have gamma and beta,
Yes.
tunable parameters. But gamma is just scalar factor. So it will be ignored on the next level, on the next layer, if we have a batch normalization layer after that.
No, after non-linear, it doesn't.
Well, if you use a ReLU,
Depends
for
on
example,
linearity.
it's preserved, and the multiplication by the dense matrix also preserves this
I guess
multiplier.
the question is nonlinearity after batch norm or after convolutions?
After batch norm.
So nonlinearity is right after batch normalization. So beta and gamma, they influence nonlinearity directly.
So usually you place your batch normalization layer between fully connected and non-linear.
Yeah, but for the recurrent, for the rectified linear unit or leaky ReLU, it won't matter. It won't make any difference because you can just put the multiplier out of the.
I don't think it's right, actually, because if you have a lot of pre-activation, which is below 0.
Oh, you mean you can change the sign?
Yes.
And well, okay, that seems to be the only useful case, just to control the sign to make it.
Anyway, it's
In
just
case of ReLU,
a
yes.
simple example that can provide intuition.
Gamma and beta are used only before nonlinearity. If we put batch normalization after, we don't use gamma and beta.
But we don't
Well,
place
for ReLU,
batch normalization before or after ReLU.
okay.
Even for real case, if we have non-zero beta, then gamma is also influences.
Yeah.
Well, only the sign of gamma. The magnitude does not matter.
No,
Why
No,
not?
magnitude is also a matter.
If we have non-zero beta.
No, it doesn't matter because next might
You can divide beta by gamma. So what?
incorporate the multiplicative constant.
But you won't obtain 0 beta, even if you divide it by gamma. Yeah, let us just believe it.
Oh, okay.
You'll check it afterwards.
Okay, let's go back to our example.
Yes, but what do you want to show by this example? So what you have shown so far is that if we have batch normalization, we're invariant with respect to multiplication in our linear layers on some scalar factor.
Yes.
This is true.
Yes.
Is this an artifact of the absence of nonlinearity? If you just put nonlinearity on HA, this won't be true anymore.
Yes.
Because no.
No, I want to show that the parameterization with batch normalization, why it can be very powerful. So here, when we compute the gradient with respect to C of our loss, it will only depend on C. And in this case, it depends on all other parameters.
Wait. In this case, you try to compute the gradient of loss with respect to A. And you have obtained that this gradient also depends on B and C. And you have claimed that this is something bad.
I'm wrong. So here we didn't change A at all, and the A parameters no longer depend on the input of last layer since batch normalization. The mean and variance.
Can you repeat?
Here you're simply obtaining a 0 gradient with respect to A.
Yes, because of
Invariance
everything,
with respect to multiplication of scalar factor.
Yes. But here we can do it on
To
this
me,
way.
it just means that if you put batch normalization, it somehow cancels out multiple linear layers in a row. So you just shouldn't do it.
No. They can be in the they can
Without batch normalization, is there any point of having several linear layers?
Well,
Without nonlinearity.
it depends which ones. Convolutions of with receptive field 3, like all modern convents do that. They stack this usually through.
Yes, but this is done only due to computational efficiency.
okay.
No,
Okay,
less parameters.
Less parameters, yes.
It's
Again.
okay. Let's move on.
The next example.
No. So okay, batch normalization guarantees that before every layer you will get zero mean and the unit variance of your activations. So and here are some plots as accuracy score versus iterations, training iterations. So the black dot is inception without batch normalization, and blue one with batch normalization and actually bigger learning rate step. You can see that we converge 6 times faster and achieve better accuracy score. So, okay. And let's move on to probabilistic view, to what we actually did. So, from forward pass of batch normalization, from this formula, we can note that the forward pass in our batch normalized network for now depends not only one object xi, but on an entire batch. Our likelihood function, which parameterized by neural network parameter theta, depends on entire batch. For every object in the batch, it depends not only that object particular, but on entire batch. And this depends can be parameterized with statistics, which computed over the mini batches.
What do you mean by without I? Batch without I.
Batch without I is batch except one object. So it's batch except xi.
Yes, but this formula actually depends on the batch itself.
Yes.
I mean, mu and sigma.
Yes, yes.
So why it is without I?
I just split them notation.
So that you
It's all
don't
about
depend on
notation.
why
How
I.
convenient for the future patients.
So I want to
If you're happy with it.
I want to know that it not only depends on the xi, the prediction of the model, but on the other objects in the batch. Okay, and during training, we can randomly choose these objects to fill the batch, and this randomness actually induces the distribution over over statistics mu and sigma. And since having the batch, we can compute all statistics in deterministic way. The distribution over statistics with given xi can be follows. It's just the expectation over all possible batches we can choose from the data of delta functions centered on mu b and sigma b. Okay, and we can treat our statistics as hidden variables in our neural network. So, and to compute actually the likelihood of the answer with respect to object X, we need to marginalize them out. We need to take account all possible statistics with respect to this distribution. Okay.
What is theta?
Theta is a parameters of our neural network, which parameters likelihood. Look, it's like we have classification problem, and at the end we have softmax.
Theta are the weights of the neural network.
Okay. So, and following.
So y is the final output, or is the output of this layer? So we're talking about just one layer, or like
No, about entire network. Mu sigma is the statistics on each layer. On all layers in our neural network. Any question here? Okay. And following maximum likelihood approach, we need to maximize this likelihood with respect to parameters theta. And the objective look as follows. Sum over all objects, logarithm of marginal likelihood. But this expectation here is actually intractable. Since we don't know exact how exact look like this distribution. So and we can't propagate gradients or to optimize actually this object. So we can use Jens-Shannon inequality and construct the lower bound for this object. Since the logarithm is concave, we just switch expectation here with logarithm. So, but still, the distribution over mu and sigma depend on parameter theta, because mean on particular layer of course depend on all previous parameters. Okay, and we cannot propagate gradients through the expectation, but we can use kind of reparameterization, since the definition of distribution over statistics. We can we can raise the expectation not over statistics, but over the mini batches. So, given the mini batch, we compute statistical analytically. And when we draw a mini batch from the training data, we draw the samples from our distribution over the statistics. Okay, and now we can propagate gradient through this expectation and use like one sample Monte Carlo estimation. And here we can compute gradients because it's just forward pass of our neural network. And that's actually what batch normalization do. They pick a batch of objects from training data, and for each object in this mini batch, it performs one sample estimation of this integral, this expectation, using the same batch actually, and it gives us the unbiased estimation of full gradient of lower bound.
Which is not variational, right?
No, not variation.
So it can be arbitrarily better.
Yes. And that's mean when we train a neural network with batch normalization, we actually maximize, it can be seen as maximizing of lower bound of marginal log likelihood in proposed probabilistic model.
And why can't we maximize incomplete likelihood directly?
Because of logarithm here, and this expectation is interruptible. So we actually can take into account all batches.
And we can't substitute it with Monte Carlo estimate,
Yes,
right?
yes.
Because it will cause bias.
Yeah.
And in order to get rid of the bias, we need to move logarithm inside, then we can use Monte Carlo estimation.
Yes. Okay. When we
So is the third formula correct because of the particular choice for the joint for mu and sigma?
Yes.
The delta point?
yes, yes. So to address the okay, and what actually is the difference between batch normalization and proposed probabilistic model? The difference is in test phase. So during the test, during the inference, we want to pass through the network. We want to make prediction for single object. But batch normalization during test use running average statistics, which can be seen as an approximation for population statistics. So, and actually it can be seen as an approximation of marginal likelihood of this expectation with this guy with likelihood in populated one statistics. Okay, and this estimation is actually biased.
Why?
We can take the expectation and see that it's biased.
Well, what is the reason for this bias?
Because we don't sample. We just propagate the expectation into the non-linearities in our neural network. So, to address this drawback, we can use Monte Carlo approximation for this expectation. So, and we need to sample from this distribution. And to draw sample from this distribution, we need just draw samples, draw batches from our training data. So the same representation as for loss function we did before. So, and Monte Carlo estimation for measure likelihood looks as follows. But there is some inefficiency here actually, and what is actually is, can you see?
Yes.
I'm pretty sure that you can see, but maybe someone else can see what is inefficient in the last.
Why this procedure is inefficient?
To compute
As batches.
for different batches.
It has different mini batches for classifying just single object.
And also we do need to store the whole data set here. Because we need to draw mini batches from it.
Okay, yes, this simple formula is very inefficient in practice.
Well,
High
can't you just
computational
store
cost.
as mini batches?
You
Like,
can-
and
you-
say that they're guaranteed to be random?
Guaranteed.
Chosen when random die?
Yeah, yeah, yeah.
Okay, yes, we need a lot of paths through the network of mini batches, not single objects, but entire mini batch. And we need access to the training data, and no one want to store their models with training data. We want to model parameters, capture the information that the hidden information from the data, and that's actually what we can do. We can parameterize this distribution and trying to estimate the parameter of this approximation. So, and we propose to approximate this distribution with fully factorized normal distribution for mean and normal distribution for variance. Okay, and we will adjust these parameters, and on the inference stage we need just a sample from this distribution, and we don't need to pass entire batches through the network to estimate for Monte Carlo estimation. Okay, and to adjust the parameters of our approximation, we use divergency between real distribution and our approximation. And this is actually our approximation line to the exponential family. This optimization problem corresponds to just moment matching.
Please pay attention that here we're using different Kell diversions, not the one which we usually use.
Yes.
There was a question from
First one.
you.
Okay.
Today you asked me about different order of Kell divergence on the lecture. No?
It wasn't me.
Was it?
Okay, and this procedure actually doesn't affect training of your deep neural network at all. You just need to capture first and second moment of activation of mean, and just estimate the parameters using those estimations. So it can be done efficiently. So here you can see the marginals of true distribution over statistics, the mean at the top and the bottom for variances, and the green one is our approximation. No, okay, it fits the real distribution well, the real marginals well.
Is it log sigma or just?
No, just sigma.
And this is log normal
Log normal
distribution?
distribution.
Mhm.
Looks as normal.
But
Okay.
what about the joint?
Jordan's distribution is highly dimensional.
No, I mean
Okay.
nu and sigma. It's two-dimensional. Because here you match the moments, and it's clear that you do it right for each one dimension.
It's actually depends on the family. So I want to show that the family is right. here.
You don't show because you need to show
The family.
the joint of mu and sigma.
Yeah, you
The
show.
family for marginals. So if I approximated this distribution, which looks like normal, with the uniform one, it didn't fit well the normal distribution.
Well, you want to approximate it using uniform distribution.
I don't know.
The question is to plot to make two-dimensional plot, one mu versus the corresponding sigma, and to ensure that the dependencies are negligible between the two variables, so you may efficiently approximate it using factorized distribution.
Okay, but even for two-dimensional interactions, so this distribution is actually over all mu and sigma on all layers, and we can actually just pick two, one mu and one sigma for one hidden unit, but it don't show the whole picture.
But like,
Okay,
for
as
other correlations between corresponding mu and sigmas, which you throw away.
Yes, there are some. Sometimes there is correlation. Yes, but I tried to capture this correlation between sigma and mu for one hidden unit. It didn't help any. So it doesn't matter. So. And the first part of how our work called is uncertainty estimation. So let's look at the problem of uncertainty estimation. Okay, let's consider the problem of training a classifier which classify cats and dogs. With some neural network, for example VGG or LeNet or whatever you want. So, and we train our neural network on training data, and it performed well. So it's like 99% of accuracy. So, but we want to good model will produce uncertainty estimation on out of domain data.
What do you mean by uncertainty estimation? What does it actually
so
mean?
we want to our network be unconfident in their predictions. So here we can see that the neural network is very confident that some picture is dog. Okay. And we want to, when we feed, for example, the image of the car, the neural network produce unconfident predictions, like the uniform distribution over the classes, with high end.
Cat and dog, but it's okay for car.
But what we actually see when we feed such neural network the image of the car, it predicts dog or cat with high confidence. We call it 0.9 probability.
Have you tried to just calibrate your probabilities? Just add temperature to softmax and tune that.
Yes, there is different options to address this issue. Okay. And one option is to use some stochasticity inside the neural network. For example, we can use dropout or multiplication of normalizing flows and forms the ensemble of models with shared parameters, actually. And it actually addressed this problem, and the distribution, the predicted distribution on out-of-domain data looks like uniform, for example, with high entropy. Okay, but dropout and multiplication normalizing flow work well with shallow model like BGG and LeNet. And sometimes we need to go deeper and train to residual network. And residual architecture, we don't have any dropout or multiplication normalizing flow layers because it performs well and accuracy degrade.
Accuracy degrade if we use some stochasticity like dropout inside this network.
Yes, inside this particular architecture.
Have you checked it? Is there papers?
Yes, the original papers on ResNet
Yeah.
tried to add dropout.
In wide digital networks, you can use using dropouts improve
Yeah,
accuracy.
yes, you can, but we talk about this.
Okay, but this architecture and so every deep architecture actually use batch normalization. And as we saw, batch normalization use some stochasticity. So we can use here stochastic batch normalization and address this issue for residual networks. Let's move on to our experiment. Here, for this experiment, we took a CFR10 dataset and randomly picked 5 classes and trained neural network only on 5 classes, on objects from first 5 classes, and then estimate the entropy of prediction, and the entropy can be treated as a measure for how our network answers their prediction.
What is entropy CDF?
What it is?
On the plot you have entropy CDF. I don't know what entropy.
Of predicted distribution.
What
Entropy
is
of which prediction is a random variable. We can build a cumulative density function for it, and we can plot it.
No.
But the label said entropy CDF. I don't know what entropy CDF means. I know what.
I now explain.
Okay.
So we have predicted distribution at the end of our neural network. Okay, we can compute the entropy of this distribution, and it gives us the measure of how our network uncertain in their prediction. So high entropy, it is very uncertain in their prediction. Okay, and we want our network on out of domain data have very high entropy, like uniform,
Okay.
which is the maximum. And here we estimate the entropy of predicted distribution for objects from 5 classes which neural network didn't see.
So these are typical objects, right?
Yeah.
And we would like to have as large as possible, have the value of entropy as large as possible.
Yes.
So this is just entropy of predictive distribution
Yes.
without any CDF.
Great.
So we have a lot of objects, from out of domain data. Okay.
For each we have the value of entropy.
Yes, and we have for each the entropy, and we plot the CDF of.
Now, this is exactly what I was telling about. We treat entropy values as a random variable, and we go against that cumulative density function, CDF.
Okay.
You actually need to explain this better in the paper, because I had a question about this, and now Tom has a question about this. So
Yes.
it's very like.
It's like you plot entropy against entropy, and it's like.
Have you tried to do some standard, maybe some standard plot for calibration? Like, is this like kind of plot? Did you come up with this kind of plot, or like is it something standard? Is it something standard?
I have never seen it before.
I actually didn't get it.
Standard way to measure uncertainty, and
Do
many
something
papers use
so
it.
that you use such brackets.
Yes, of course. So when you trying to address uncertainty measure problem, you actually do it.
It's very popular.
Multiplicative normalizing flow, they did it, and in a deep ensembles method, they did it.
papers that try to estimate calibration of the probabilities to actually measure if the probabilities are good or not, they do different kind of plots.
Yes, but they're trying to solve different kind of problem. They're trying to make probabilistic calibration.
Yes.
Here we explore only the interval.
But can't you, like, if you just add, like, I'm trying to understand that this entropy make sense. For example, if you just add a very high temperature into softmax, kind of flatten out all your probabilities uniformly, will you get ideal plots out of this or not?
Yes, of course, we will have with ideal plots. But we should also control the accuracy or negative log likelihood.
This won't change accuracy.
Negative log likelihoods are okay. And we control the negative log likelihood.
This will improve negative log likelihood, like to an extent. Like, okay, if you put very high, it won't improve, but like there is a sweet spot, which is much greater than 1 on these networks. So it's like.
But this is usually where we converge. We optimize negative log likelihood.
Usually negative log likelihood overfits like crazy, and networks are overconfigured.
So if we add temperature now softmax, it destroy. We will end up with a bad negative log likelihood score.
No, because you will improve negative log likelihood compared to not having temperature.
No. That depends on what data set will we use for setting the temperature. The same training data set or the data set where we have classes which were not contained in training data.
Well, what I know is if you set the temperature using the same, the validation set of the from the same domain, if you set the temperature properly, you will improve negative likelihood a lot.
Okay.
You will solve the issue of overfitting in terms of negative likelihood. Not solve, improve a lot.
I think I get you. May I answer?
You get rid of being overconfident.
If we adjust temperature in this way, okay. Let's move on. Okay. From our observation, we want to entropy be high on out-of-domain data. This means the lower plots and the lower curves and the righter the better. Okay, for these plots. The green curve corresponds to dropout, just simple binary dropout. Deep ensembles for deep ensembles, which means just we train a fixed neural network from different initialization and form the form ensemble. Okay, and the blue one is for stochastic batch normalization, which actually ends up with the most confident predictions on out of domain data on seeing data. Since the product and deep ensembles don't contradict with our method, we can add a stochastic batch normalization procedure for dropout and deep ensembles, and we can see that it's actually improve our uncertainty estimation.
If you just add temperature equal to 2 bucks, will your curve like go down like everywhere?
Okay. I again trying to answer your question. If you adjust temperature in the way you described, like maximize the negative log likelihood on the test score, you don't end up with a very high temperature. Okay, and your plots here. Okay, and your plots here don't actually end up with the highest possible entropy everywhere.
Yes, but temperature will go like the right direction. So it's a question like how much will it go? So it might go just it might be way better than any of this method. You just don't know.
Let us see. So temperature calibration is some kind of additional procedure, and here we obtain uncertainty estimator end to end using the same training data.
So, for example, for this procedure, you need some validation set or training. You can't.
You need validation set anyway.
Yeah, but you
work without validation
But you
set.
can't train data on all data that you have. You have to split your data.
You always need to have validation set anyway, no matter what you use. You have to validate. How are you choosing your step size?
Okay, you can validate and choose like hyperparameters, and then use this hyperparameters and use all data that you have to train the model, which you deploy.
Usually that's a bad approach. You get screwed. Hyperparameters.
But when we test on the data from our domain, our target domain, how this entropy CDF looks like? Is it the same?
No, the curves almost all entropy is near to zero, like this.
I think when computing accuracies in the final table, which is probably the next slide, were they using just one sample from the distribution, or they were averaging over predictions several times?
For all models, the accuracy for ensemble.
For ensemble of, okay, for this kind
We
of
sample a
several
lot of
samples.
samples.
How many?
Like,
Could you please show
50?
again the previous plot? So SBN is allocated to the left and to the up, right? And this is for the objects from around classes, from the classes which haven't been contained in the training set.
Yes.
But doesn't mean that this is a bad result. Yeah.
The
So
left part
we
to
can-
the left?
Because we need the highest possible value of entropy
Yes.
for the wrong classes. And here, what we have the
The high,
We need something like this, but we can't do it.
Yeah. Yes. Yes.
So
Okay.
we are like better than other
You-
methods.
if we use just stochastic batch normalization, we end up with the most overconfident. But we can improve dropout and deep ensembles, add the stochastic batch normalization, which considers the dotted lines here.
good.
Have you tried to ensemble dropout?
It's all for ensembles. We ensemble
You have dropout plus SBN, deep ensembles plus
SBN.
SBN, but deep ensembles plus dropout. Do you have that?
Actually, no.
Is it possible?
Why not?
So in case of no SBN for SNAP
Then
in
we
the final
need to
table,
do
was
it,
there no
And then to combine deep ensembles, dropout, and SBN.
What is the consensus?
in the table in case for no SBN resnaps, there were no uncertainty there whatsoever, right? So it was not an ensemble.
There's all for ensembles. SBN with sample statistics.
Yeah, but no SBN just sample of ensemble of neural networks. Or what?
No
Piece of-
SBN here.
In case of no SBN, is it an ensemble or what?
Nothing. It's just
Ah,
nothing.
I see. So we get. I see. So it's like the SBN take like a factor of 10 times longer to predict, right?
Then just one model.
Yeah, the SBN is heavier from computational perspective by a factor of number of samples, right?
Yes, but so actually, if we have to make prediction for one object, we can do it in a single pass because we can sample a lot of statistics for one object on intermediate layers and pass them through the network.
Yeah, but you pass them, you don't average them, right?
I average the predictions.
This means that
yes.
you'll have to make several passes.
Okay, not several, but maybe one batch parallel pass.
Yes.
But this batch parallel pass, unless you have an infinite GPU, if you have it, you can pass where you store it. It would still take a lot. And sorry, if you just take one sample or average, whichever is better, what happens with the accuracy? Does it degrade a lot, or
One sample for entire batch.
for the SBN? Yes, for one training example, you only sample the mu sigma batch normalization variables once, or use the maximum likelihood for them, the approximations.
The accuracy didn't degrade.
At all?
For SBN, just SBN.
For SBN, yes.
For SBN with one sample, without ensembling.
With one sample,
This was the question.
Okay, it depends. It can degrade a little bit, so not huge degradation of accuracy.
This is
Go ahead.
no,
It's
just
like degrade here a little bit.
because I mean I might be incorrect here, but KIFAR 5, for example, has a test set of KIFAR 10 divided by 2, which is like 5,000 examples, and 1/100% of error is around one sample there.
Okay.
So, I mean, when you say it may degrade a little bit, what's the extent of this little bit? Is it just 1%, half a percent, 0.1%? I mean, the typical value, just if it degrades, how severe it is.
I mean that you can sample different value for statistics, and you end up with different score. It can be higher or lower.
Okay, I see.
What is the variance?
I don't remember.
Okay. So,
Like all zeros in STD is suspicious. Looks like a bug.
So it's for ensemble. When you ensemble, you
But this is STD with respect to what?
with respect to different samples.
With respect to different samples or ensembles?
Ensembles.
Ensembles. So for ensembles, the variance is, can be pretty low.
Okay,
How many ensembles did you do? Like five ensembles?
50.
50 ensembles.
50 ensembles of
50
size.
samples,
I don't know how big is each ensemble.
Uh,
Are those are different networks or like
Each
I sample
ensemble.
50. I sample statistics 50 times.
So one ensemble
It
has 50.
consists of
Models,
50
yeah.
models.
How many ensembles did you have?
Like 50.
50 by 50.
Yes.
50
So,
by 50.
Yes.
did you do any study on how the uncertainty estimation works depending on the size of ensemble? Like, if you have just 10 models in your ensemble, if you sample just 10 times, or 30 times, or 100 times, how many times is enough? When does the model stop improving?
50 enough.
I mean, but I want the plot.
This is your favorite number.
Yes. So it's like I looked on this plot. How accuracy depends on how many times I sample statistics,
Okay.
and it was 50.
But that's accuracy. What about the uncertainty estimation, the CDF of entropy?
I didn't.
I mean, it's an interesting study for anyone reading the paper.
We just believe that 50 is more enough.
Tell that to your reviewers, okay?
another strange question for many other uncertainty estimators like Bayesian neural networks, like stuff that estimates uncertainty. It's sometimes possible to sacrifice only a little quality but win in terms of performance if you stack a lot of non-uncertainty aware, like normal, in this case normal batch normalizations in first several layers and only apply stochastic batch normalizations at the top. So you just compute the deterministic body and then sample from the head several times. Does this trick work for the batch normalization? And if so, what's the entropy plot for this case, if you know anything like this?
So we didn't perform those experiments, but for stochastic batch normalization, as you can see, we have low entropy.
Yeah, but it's
And this is because of the distribution over statistics are not wary enough. So
they have insufficient variance, you mean?
yes, and we need to we needed to use batch size like 16.
Or less, you mean?
With less batch size, we end up with worse accuracy.
So you mean you
But
have
with more diverse distribution.
Yes, but
So I have two questions. First is, how does batch size influences your results?
it's actually an interesting question. So with smaller batch size, we end up with distribution with bigger variance, and our ensembles is wider. So it's like
small batch is better for uncertainty estimation.
yes, but it's crush the negative log likelihood score and the accuracy.
The second question is following. Like in real life, in tasks like semantic segmentation, your batch size is very limited by available GPU memory. Is it right that using your parametric approximations for statistics of standard deviation and mean, it is possible to sample not from real, but to use virtual big batch size,
use several patches of the images.
Use several batches of the images to compute statistics that would be present if your batch would be big, and then use these statistics to train the model, to emulate
virtual batch normalization. Yes. So you describe.
There are three things under this name, and two of them are not what we're talking about. It's more like a semi-instance normalization, semi-batch normalization.
When you use not the statistics computed from the batch, but some statistics computed from the parametric model, is it possible?
The suggestion is, can we kind of predict true statistic instead of batch statistics? Can we do better if we try to do it? As I understand it.
Yes. Because it's very painful to train models on batch size too.
Maybe it sounds very cool. You can try it. You didn't try it, but it's a really interesting suggestion.
You suggest to use a model to predict statistics on each layer.
So you can your model consists of two parts. First is your neural network, and second is batch normalization statistics predictor. You can do several forward passes to aggregate a lot of statistics. For example, imagine your GPU allows you to train on batch size 2. But you can do 10 passes and compute 20 statistics. Then you can use these 20 statistics to feed your second model that predicts the distribution of the statistics. And during neural network training, you can sample from this parametric model instead of using your batch statistics. And it seems like it will allow you to emulate big batch size without sacrificing performance very much.
It's interesting model, but when you train your neural network, your parameters change. And
you can repeat it every 100 iterations.
Yeah, okay, but so it may make sense, but it have high computational cost. So you need to pass 20 times batches after each iterations of your stochastic gradient descent.
I believe improvement in convergence speed will
maybe.
I think this is a very good point. So maybe this is an area where this model can be really applied and where it has no analysis because of this limitation on the mini batch size.
Yes.
Yeah,
so,
that's very interesting.
There's also another very recent paper called batch Kalman normalization, which is another idea on how to use something like batch normalization on very small mini batches. I think they go up to 8 or even smaller.
Can you send it to the group?
It's already sent to the chat.
Okay. So in this work we propose a probabilistic model which consists consists behavior on test and train phases. So we propose a scalable approximation technique for inference stage, and we end up with a simple and efficient procedure method for uncertainty estimation. Check out our paper on arXiv and codes on GitHub. Thank you for attention.
So you finished your talk just like a spotlight speaker on the top conference. Please check out our paper, please visit our poster.
Like, subscribe.